Hello, I'm Lance Lucero, Product Manager of Astronomy for Celestron, and I'm here with another installment of Dear Celestron, where we take the time to answer your questions about your gear. Our question today is, why does my astronomical telescope show me images that appear upside down or backwards? And what can I do about it? Well, the answer to this question will depend greatly upon what type of instrument you're using. So let's take a look at refractors. A refractor is basically a telescope that has an objective lens here at the front and an eyepiece holder at the back. Now, if you were to take a standard 20 millimeter eyepiece and insert it directly into the back of the scope and look straight through the scope, you would be seeing an image that is upside down and mirror reversed left to right. Now, by adding an accessory called a star diagonal, which looks like this, it's the L-shaped piece, kind of triangular. This could contain either a mirror or a prism, depending on the type of model that it is, but it is still effectively just a surface that reflects the light coming out of the back of the scope 90 degrees so that it points straight up. So you insert this into your scope, insert your eyepiece into the star diagonal. Now, when you hold the diagonal straight up like this and you look through the scope, you will now be seeing an image that is correctly oriented up and down, but still mirror reversed left to right. Now, this is the way most normal refractors will come. There are, however, a few, such as our Astromaster line and our Power Seeker line of refractors, will come with a 90-degree erect image diagonal. Now, this uses a very special prism called an Amici prism and bounces the light around inside of it a few times so that when the light comes out, you will actually get a 100% correctly oriented image. Again, drop your eyepiece inside of it, and now when you look through, you will see a 100% correct image. You read a street sign, it's going to look exactly like it reads to the naked eye. Most of the time, this is signified by the ball. When you see a diagonal that has a ball instead of the triangular shape, that usually means that there's an Amici prism inside, which will, again, correct the image 100%. There is another thing that is available for refractors, and that is called a 45-degree erect image. Now, this actually is still a prism, but it holds the eyepiece at a different angle. This is more useful for when you're using the telescope for terrestrial observing, where it's easier to look like this than it would be to look straight down. Still kind of lets you look up a little and see the target that you're trying to view. But again, giving you a 100% correctly oriented image. Now, these accessories will also work on other telescopes, like any catadioptric scope, or something like our Schmidt-Cassegrain or a Maksutov Cassegrain. We'll still be able to use the same accessories to get a 100% correct oriented image. This Schmidt-Cassegrain here, again, if you were to put an eyepiece in the back, just like the refractor, you would be looking at an image that is upside down and mirror reversed. Normally, a Schmidt-Cassegrain will come with a 90-degree either mirror or prism diagonal, again, giving you a right side up image, but still mirror reversed left to right. Again, to correct that, you can go with either an Amici prism or the 45-degree erect image prism. Both fit in here, same eyepieces are used, and you will still be able to get a 100% correctly oriented image with these. Now, we go on to Newtonians. Now, this is going to be a little bit different. Since a Newtonian design has your mirror here at the back, there's a small secondary mirror on the inside here that redirects the light out the eyepiece, which is at the top of the tube, not the back of the tube. Now, Newtonians are notorious for having very short back focus. What I mean by this is the amount of throw that you get when you turn the focus knobs. Basically, a very short amount from here to here is all you have in order to get your eyepiece in the appropriate spot to reach infinity focus. Prisms like these eat up a lot of back focus. So you would think that you should be able to drop a prism in and be able to focus it, but what you're going to find is that you don't have enough inward focus travel to allow the light to get all the way through this prism and still bring your eyepiece to the appropriate point so that it actually focuses at infinity. So you use a standard eyepiece with a standard Newtonian, and you're going to wind up with, again, an image that is upside down and mirror reversed. But to correct that, we have a special eyepiece that we offer that's included with the Astromaster line and with the Power Seeker Newtonians. And that is a 20 millimeter erect image eyepiece. Now, what makes this eyepiece special is that compared to a standard, you'll notice the body length is significantly longer. You'll also notice that the shoulder height here at the bottom of where this sits into the focuser, this will sit a lot lower. And the reason for that is because there is a prism, prism, which is actually installed inside this eyepiece that allows you to flip the image while it is still inside the scope, not something in between the eyepiece and the scope. And that's critical. To give you an example, I'll show you what this prism looks like. Please, I don't advise you to take your eyepiece apart to look at it. That's why we do this for you. But this little housing right here basically includes a little prism. You can see the little glass prism right there that is inserted in the eyepiece. And then when the eyepiece is put into the scope, it intercepts the light path, eliminating the whole back focus issue and allowing you to reach infinity focus. Now, one problem with this particular type of prism eyepiece is that they only work with long focal length lenses. You cannot get a higher power eyepiece that actually contains this because you don't have enough room in the body to use the prism. And a perfect example of this is the pictures that I have up now, which show you the difference between the standard 20 and the field of view of the 20 with the prism. You'll notice that the prism version has an erect image, but it is severely truncated, not allowing you to see the full field of view at the convenience of having an eyepiece that will allow you to use a Newtonian for terrestrial observing. Now, it is a little known fact that if you happen to be a contortionist or a gymnast and you're really good at this, there is a way to get a 100% correctly oriented image through a Newtonian using any standard eyepiece. And the trick to that is, you see how the Astromaster here has a tube that is set in tube rings. This allows you that when it's on the mount to basically rotate the tube within the rings to change the angle that the focuser lies at. When you use your Newtonian and the focuser is parallel to the ground and you look through the eyepiece, you will see an upside down image that is also mirror reversed left to right. Now, if you rotate the tube within the tube rings so that it is straight up and down like this, and you look through it so that your chin is pointed at your target, so like this, you will actually be seeing a 100% correctly oriented image with your eye and any eyepiece that you want to use your Newtonian with. It does not require a special eyepiece or any other accessories to do it. Problem is, if you're viewing this for terrestrial use, it's still going to be complicated and it is going to hurt your neck to hold your head in that position over the eyepiece in order to see it fully erect. However, if you are trying to use this for astronomy, good luck with that. So now comes the question, why do astronomers do this? Why do they not just put prisms or some kind of a lens system in the telescope that is actually going to make it an erect image? And there's two reasons for it. One of them is that astronomers generally like to look at faint objects like a galaxy or faint nebulosity. And the trick is you want to get every one of those photons from that object coming straight down into your eyeball. Anytime you put a piece of glass, whether it be a prism, whether it be a mirror, anything like that, when light strikes glass, two things happen. Some of that light gets bounced off of the glass. The rest of the light passes through the glass. So if you have a prism, most of your light, say 97%, will go through the prism but 3% of that light gets either absorbed or reflected by the glass, which means you are not getting all of the light through. Now, say for example, you're using a prism like this, and you have a multiple reflection on the inside plus the initial surface of the prism. As the light comes through, the first time you're going to lose 3%. The second reflection, you're going to lose 3 more percent. The next reflection, you're going to use 3 more percent. Then it gets to the eyepiece. So just by adding this one accessory, you have now gone from a full light source coming out of the back of your scope, dimmed to 91% of that total amount of photons coming through, because the rest of it has either been absorbed or rejected by the glass. The more glass you put between your eyeball and the object that you're looking at, the more chance you are of losing light. And when you're looking for the faintest galaxies, or you're looking for faint detail in nebulosity, it really becomes critical. You want to get every single photon that you can through that scope and into your eye to be able to see the detail that you're looking for. That is the reason why astronomers prefer to do away with this. Now, again, why do all the Schmidt-Cassegrains and larger telescopes that we sell come with these giant diagonals? Well, the main reason is for comfort. If you have ever tried to look on a German equatorial mountain, you had a scope that was pointed straight up. You have to get down on your knees underneath, and if there wasn't a mirror diagonal allowing you to look sideways into the scope, you would actually have to hold your head up under the scope like this. And let me tell you, if you're crouched down under a very big scope, it can be a pain in the neck, no pun intended. It is legitimately a difficult thing to do. So again, that's one of the main reasons why astronomers don't really care about having prisms built into the scope to give you a correct image. If you want a scope that is specifically designed for that, that's why there are binoculars and spotting scopes. They contain prisms as well that are built in. When you're using those for bright daylight, you have so much light to play with that if you're only looking at 91% of the light that comes through the scope, you're not really missing much. But when you're going after faint celestial targets, you want every bit of that light to come through your scope, as much of it as possible to get into your eye so that you can actually see that item for what it is. So that brings us to the second reason why we don't care if an object appears upside down or not. Simply put, we live on a globe, on a sphere, and someone observing the moon from high latitudes of the north versus someone down in New Zealand, on the same night, looking at the same moon, the moon will appear upside down with respect to each other's points of view. So in all honesty, it doesn't really matter in space if an object is upside down or not. The point is you're seeing it, and you're seeing it in all its glorious detail. So I hope that answers your questions. And again, feel free to reach out to us if you have any questions that you would like to see for future installments of Dear Celestron. Would appreciate it. Good luck, good seeing, and peace out.